Assalamualaikum warahmatullahi wabarakatuh. First of all, thank you for me for the committee of the Kuningan International Conference for me to present our research with the title of Virtual Screening of the Trimethyl 1,4-A 2-phenyldiazine 1-phenyl carbonyl thiourea as Sirtuin-1 inhibitor. And the theme of this research are Ruslan Komaiser, Richa Mardianingrum, Tita Novianti, Professor Dr. Suspandono, Yunia Sarvatingsi, and Professor Dr. Aryanwar. And for the background of the research is many cases in cancer. Yeah, there were an estimated 18 million cancer cases around the world in 2018. Of these, 9.5 million cases were in men and 8.5 million in women. So, in drug discovery needs many research for find the new compound for cancer activity. And one of the compound in research in drug discovery is Thiourea. We know Thiourea have many activities. One of them is anti-tumor or anti-cancer from the reference of Puparici, Caracus, Uan, Purtinian, Puruta, and Lee. So, Risvanto and friend design and synthesis one of the compound 1-benzoyl trimethyl like this structure. So one of the design compound as the derivative is the title compound, and now we reported the title compound in silico research. And for the method, we use some procedure. And for the in silico, we need an instrument like the PC and the software. And the software used in is Chembro, Marvin, Molecro, Autodoc, Thiourea, Readmet, and Lipinski. And for the procedure, the first procedure we done ligand and receptor preparation. The ligand was drawn in 2 dimensions using Marvin's CAD software, and then protonated to procedure uh, the age of 7.4, after which the file was saved in .mrv form. The next step is to determine the structural conformation by performing a conformation check. Then the file is saved in .mol2 form. The three-dimensional structure of Sirtuin-1 is downloaded via the Protein Data Bank website with the PDB code 4A5A. And then the next procedure we done validation and docking method. In validation of docking method, we done docking of natural ligand or native ligand is carried out to look for the 3D conformation of natural ligand to the receptor by observing the coordinate of the mass center of the structure and the Greek stock size of the binding site pocket in angstrom, which is expressed in the value of root mean square deviation. The docking method is said to be valid if the MHD value obtained is less 2. And the next procedure, we done docking the title compound. In the title compound, we done docking of the compounds against cancer receptor using the auto program. This test compound is docking to the ligand binding sites of the Sirtuin-1 receptor. The result obtained from this docking process are the lowest binding affinity. The next procedure, we done visualization of the docking result. In visualization of the result, we done visualization is performing to determine the ligand receptor interaction in two, two-dimension and three-dimension form. The best doc results are made of complex files for visualization using the biopia discovery. And the last procedure, we done the pharmacokinetic prediction. In the pharmacokinetic prediction, we done the prediction of several aspects of molecular design pharmacokinetics is done qualitatively using Lipinski rule and quantitatively using pre-arithmetic. Lipinski parameter use velocity, molecular weights, hydrogen bond donor, and receptor. The pre-arithmetic program is a web-based application for predicting absorption, distribution, metabolism, and excretion data using the in silico method. The program is accessed online through web-based server. After we done all of the procedure, we get the results, and the result and discussion, we get the data. So we just look at the table 1, data on docking result of native and test ligand. We can compare the native ligand and test ligand for the docking result. In the docking, we run in 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 100 runs, and we can compare the binding affinity native ligand and test ligand. If we compare the binding energy of the native ligand and test ligand, we saw that the native ligand get the binding energy of minus 9.74, and test ligand get the binding affinity of minus 8.61. If we compare between native ligand and test ligand, it's said the native ligand better than test ligand, but not too different. So in this case, test ligand similar activity in native ligand. And the validation method and the documented validation result was done in the condition of the grid box X, Y, Z, obtain an RMSD value of 0.374 angstrom. And from its information, the validation is valid because the RMSD has true. After that, we get the two dimension of the docking result for visualization our docking. And from the two dimension, we show from the native ligand, we get three hydrogen bonding. And some of the hydrophobic, 1, 2, 3, 4, 5, 6, hydrogen, 6 hydrophobic interaction. And for the test ligand, I think similar, we get three hydrogen bonding, and hydrophobic interaction, we get 1, 2, 3, 4, 5, 6 hydrophobic bonding. And if we compare the hydrophobic bonding, so we saw the ligand much more in hydrophobic bonding. After that, we get the pharmacokinetic and toxicity prediction. The data of pharmacokinetic and toxicity prediction we get from the pre-admit is a server. The pharmacokinetic parameter used were CaCO2, human intestinal absorption, and plasma protein binding. And we can compare the pharmacokinetic and toxicity of native ligand and test ligand. And we look one by one. Native ligand get CaCO2 of CaCO2, HIA, and protein plasma binding. I think the native ligand and test ligand almost similar. So the absorption and distribution condition between native ligand and test ligand is same, not too different. And if we saw the toxicity prediction from the AMES test and carcinogens, I think the native ligand and test ligand is the same too, but the different in carcinomouse, native ligand is positive and test ligand is negative. So in the carcinomouse, the test ligand is better than native ligand. This is the limited of the parameter of the pharmacokinetics. Example, CaCO2, low permeability if the data get less than 4. Middle permeability if we get 4 until 70. And high permeability more than 70. If we look by the percent protein plasma binding, chemical strongly bond, if we get data more than 90%, and chemical weakly bond, if the data we get less than 80% from Yamashita, Yi, and Zhao. And then we get to physicochemical properties according to Lipinski rule of 5. In this data, we also can compare the native ligand and test ligand by molecular weight, donor hydrogen, acceptor hydrogen, log P, and refractory molar. And just we look at the native ligand, molar weight is 2.0, yeah, and test ligand is 298, and donor hydrogen native ligand of 3, and test ligand 2, and acceptor hydrogen native ligand of 2, and test ligand of 5. And the final under refractory molar and the native ligand, we get the 72, and the test ligand we get the 686, and I think we compare between the native ligand and test ligand. It's according to Lipinski rule of 5. So based on the physicochemical properties test result in table above, all of the compound between native ligand and test ligand would comply with the rules, so that this compound can be used as drug candidates for oral use. And for the conclusion, based on the results, it can be concluded that Thiourea has activity as an anticancer by inhibiting the Sirtuin-1 enzyme with a free energy binding value of minus 6.8 minus 8 0.61 kilocalorie per mole. From the results of pharmacokinetics and toxicity prediction, the test ligand have better results than natural ligands because natural ligands can cause carcinoma pains. Although the test ligand has mutagenic properties, its use as an anti-cancer drug must be reconsidered for its safety. And uh, I don't forget for the acknowledgement for the penelitian pasca Dr. Grand Universitas Indonesia from the Ministry of Research and Technology, BRIN. And I thanks to Stikes DTH and Guntur for the provision of the facilities to complete our research. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.